Yes, good morning to all. Welcome to the second day of our WIM 2025. Yesterday, we have seen spectroscopy and the facilities at IIT Madras. Okay. And we have missed yesterday CSR NML visit due to the lack of time. It is mostly maybe in 6th, we will be going early and we will try to see both the centers in 6th visit. And now I would like to introduce today's speaker, Kunash Instruments Managing Director, DK Sharma sir, and who is supporting us continuously from 2016 onwards. He is supporting, and when we have initiated our WIM, and he is the person who encouraged us to go ahead, and he has sponsored and he has given confidence to us to conduct this WIM 2017. At that time onwards, we are conducting this, and we always require his wishes. Thank you, sir, for your support. In this small introduction, just I would like to hand over the session to you, sir. Thank you, sir. Please, sir.
Thank you, Professor Chenna. Okay, as very slight correction, I was or used to be managing director of Kunash Instruments, who were marketing micromeritics products in the country, I think for last 30 years. Today, the situation is slightly different. Micromeritics is we are owned by Micromeritics. That means Micromeritics holds our company, holds the stocks of our company. So we are Micromeritics in India. But another change that has taken place is now Micromeritics is part of Malvern Penn Analytical. So now these three companies are together: Micromeritics, Malvern, and Penn Analytical. The company which basically Physics Analytical, Philips Analytical company. So today the situation is Micromeritics, Malvern, and Penn Analytical. These are three companies together. And for the first time, I come here without shaving because I wanted to show off that I'm near my retirement. Okay. Anyways, we'll continue with studying texture of our materials. And the texture is surface area and pore structure. We are not talking about the general roughness. We are not talking about other chemical nature of the surfaces. We are purely talking about surface area and porosity studies of your materials, whether they are in powder form or in chunks or in bulk form. We'll try and measure their surface area and pore size or porosity, for which all of us know that we use gas adsorption as a method. Now, just to tell you how gas adsorption helps us is, see, surface area is basically calculated, not directly measured. It's calculated by putting few units on the surface, covering the entire surface once, that is in the monolayer form, counting how many units have been used up in making one layer, multiplying this number with the cross-sectional area of the unit will give us surface area. In a sense, that is what it is. You can see, I don't know how many the backbenchers can see, basically the number of units used multiplied by the cross-section of one unit gives us the surface area, dividing by the weight of the sample or mass of the sample gives us the specific surface area. Others are only constant to convert volume into numbers and those sort of things. Adsorption is not a new phenomenon to any one of you. The interparticle forces that are normally responsible for bulk properties of any material, these forces are not quite saturated on the surface. And this unsaturation or this imbalance of these forces makes the surface slightly more active. Okay. As far as adsorption is concerned, these surfaces are ready to attract any molecules or any atoms that approach them. This is the imbalance. They are the same forces which are responsible for condensation. Okay. These forces are given the name of van der Waals after the name of the scientist who probably discovered them. I don't know whether you will be having access to these slides at any time, but this is what I have been talking to you. Okay. I'm sorry about this. When I wrote it or when I edited it, it was all right. I don't know how it is looking different here. What it basically means is the amount of adsorption of any given gas on any given solid. Or let me put it on any given mass or unit mass of a given solid at constant temperature is proportional to the pressure. That's all that this equation says. N equals function of P by P0. Outside the brackets are temperature, gas, and solid, which remain constant. So once again, amount of adsorption, that is N, is a function of amount of adsorption of a given gas on a unit mass of a given solid at constant temperature is a function of pressure. That's what this equation is. If we are working at temperatures which are below the critical temperature, then pressure can be expressed at relative pressure, which means pressure can be divided by its saturation pressure and used. The reason why it is divided by saturation pressure is number one, we wanted to generalize the adsorption phenomena so that if you are adsorbing nitrogen or if you are adsorbing argon, it shouldn't matter. And the second reason is, after we do the measurement, most of the theories that have been developed, which will be applied, contain this P by P0 ratio, not just the pressure. So that's the reason pressure has been expressed at relative pressure. At constant temperature, relationship between volume, because it's a gas, so the measurement will be in the form of volume, which will then be converted to numbers. But measurement is that of volume. So volume and pressure relationship at constant temperature is isotherm. So this is the adsorption isotherm that we are talking about. Gas adsorption experiment or the instrument, it does only these things. Okay. It gives you surface area, it gives you pore structure, it gives you adsorption capacities, which are very, 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 very useful topics nowadays. And then chemisorption, a phenomena used to study the catalysis behavior, and we are not touching upon that during this. This is how it is done schematically. You have, can we switch off these lights here? Lights. Yeah. You have a tube, sample here. The sample tube is kept in coolant, okay? And of course, Devor, which keeps the coolant. The sample tube is connected to vacuum. It is connected to the gas, which will be adsorbed, known as adsorptive. So if it is nitrogen gas that we are adsorbing, nitrogen will be adsorptive here. And a transducer to measure the pressure. Essentially, there will also be another line connected to helium gas. I don't know why I missed on that. The procedure is simple. Evacuate after you have cleaned the sample, evacuate it. Once it is completely evacuated, measure what is known as free space, and free space is any space within this volume besides the sample. That's the free space. Measure free space, because for measuring free space you will be using helium gas. So once again, once the free space is measured, next step I believe is a measurement of P0, even that is not been shown here. The saturation pressure has to be measured. And then again evacuate and start the adsorption. Okay? Remember the classical method of measuring adsorption. The measurement is only that of pressure. We are not measuring volume adsorbed. Volume adsorbed is a calculated quantity. It is calculated using gas laws. And remember, I told you we have to measure free space. Gas laws, the volume measured quantity is calculated by finding out how much gas was sent in and how much remains unadsorbed. How much gas was sent in minus how much gas remained unadsorbed is the volume adsorbed quantity. In order to calculate unadsorbed, we need the measurement of free space. And since part of the free space is inside the coolant, which means it's cold, and other part is because the pressure is being measured at the room temperature. So part of the free space is cold free space, and part of it is warm free space. And the reason why both are measured separately is because in colder regions, especially at their liquefaction temperatures, no gas is ideal. Okay, gases are not, most of the gases will be ideal at room temperature, but nitrogen gas at liquid nitrogen temperatures is not an ideal gas. So we have to, in the colder zone, we have to apply a certain correction factors in order to take account of the fact that it is not ideal gas. Okay. same thing which I have told you. I don't know how many of you are doing gas adsorption measurements. Can you raise hands? How many of you are doing gas adsorption? All of you, at least those who have done the gas adsorption, must have seen some figures like this. They tried to adsorb various gases on various type of solids. And they found that all isotherms are one of them. Okay. The last exercise, if you have heard me in any of my last lectures, would have shown you only 6 of them, not 8. These are classifications made by IUPAC. Okay. Their recent meeting was between 2009 and 2015. The earlier meeting was in 85. So those 6, and they are not the first 6. Today you are seeing 1A and 1B. It used to be only 1. One first, second, third, and also you are seeing 2 of 4A and 4B. It used to be only 4. So first, second, third, fourth, fifth, and sixth. These used to be the classifications earlier. Of course, 85 is too long back a period. After that, a lot of new materials have started finding uses, and they have been invented, and they thought that it is necessary to include those representative, include those isotherms which are representative of those new materials. So 1B and 4th B have been added. Okay. Both 1 and B are representing microporous materials, as you know. The difference is that 1A is having very, very small micropores. You know that micropores are any pores less than 20 angstroms or 2 nanometers. So 1A is representing materials which are all having pores of smaller than 2 nanometers. Both 1A and 1B represent materials of pores less than 2 nanometers. The difference between them is 1A represents very, very small micropores, and 1B represents slightly wider micropores. Very, very small micropores means pores less than about 8 angstrom. And 1B means pores which are larger than 8 angstroms. It makes a lot of scientific sense to get them represented by different isotherms because the mechanism of pore filling in a smaller micropores and larger micropores are slightly different. When you have, because I won't have detailed slides on micropores, this thing, but let me tell you at least those things. These are what is known as ultra micropores, pores less than about 8 angstroms. If you remember, we are talking about nitrogen adsorption. Nitrogen molecular size is about 3.5 or slightly more than 3.5. If they were to sit on the walls of a micropore, you will at least require 7 or 8 angstrom so that one molecule gets inside. In such cases, while of course, both in 1A or 1B, It's a diffusion that takes the molecule down inside the pore. But if you consider the walls of the pore, in 1A, it is the solid and fluid. I'm talking about nitrogen molecule and the walls of the material. Those attraction is prominent. While in the case of 1B, pores are wider. Here, the interaction is prominent between fluid. I don't know how many of you have heard of Cooper, Bardeen, Cooper, the famous people who gave the mechanism of superconductivity. Out of these 3 persons, BCS, out of these 3, Cooper was responsible for giving a notion of cooperative or cooperative forces that enhances the potential. And that's why it is those fluid interaction inside the pore that enhances the force of attraction between nitrogen molecule and the pore. Second one is that. So it's all these things have been subdivided from what they were in 1985 based on some scientific reasons. Another difference comes in do I do something wrong here? Okay. Comes here is this one. Both are porous materials, especially mesoporous materials. But here, the pores are larger, and here the capillary condensation starts taking at a very low pressure, comparatively speaking. So here the capillary condensation is at this place, here it is at this place. It results into 2 things. First thing is that the normal methodology that we used for measuring pore size distribution for mesoporous materials didn't quite work the way it should have in the case of 4B here. Anyway, since we will be talking about those mesopores analysis, I'll talk a bit more about it. Okay. Quickly, we will go through some of the methods, some of the theories, some of the modeling that goes. Remember, our purpose is to find surface area. And as I said, for calculating surface area, we need to know how much volume is consumed in making a monolayer over your samples. So finding that monolayer capacity is important for calculating surface area. The first theory came from Langmuir. And luckily for Langmuir and the people around him at the time, the modeling that he worked on or he came out with was quite successful for microporous materials. And fortunately, because he was working on carbons and trying to prove whether the theory is good enough using carbon materials. And as you know, carbons are microporous materials. The theories worked nicely. But when it was applied, once again, I'm sorry, I think when I copied this onto my flash drive, some of these equations, otherwise, you believe I would have made a slide like this? No. But it's a BET equation you'll find at many places. It's a BET equation. That is the second modeling that came about because the first one didn't work on many other materials, or most of the other materials. The first modeling was based on few facts or few postulates or few assumptions. Most of those assumptions were also part of this BET modeling, except one. The first one limited the adsorption to the first layer. The Langmuir said the adsorption is limited only to the first layer. There is no further adsorption. BET, these three gentlemen thought it can continue and form multi-layer. And that was the difference, main difference between the two. They came out with this equation. The equation is a linear equation and was allowing you to calculate monolayer capacity from an experiment which included multi-layer formation or multi-layer adsorption. So from an experiment which consists of multi-layer, you are able to now calculate what is the monolayer capacity. This is the y axis. This is Py P0 is the x axis. Beta is the constant, which is the y intercept, and alpha is the slope of this straight line. 1 over slope plus intercept is your volume in the monolayer. Okay, and from there you can calculate surface area and everything else. A constant C is quite important. Okay, a constant C is very important, which is an indication of the energy of adsorption. Okay. Remember, BET allowed multi-layer adsorptions. So when they started writing the equations for first layer, for second layer, for third layer, in each layer, this energy came into the equation. Now, summing up all these things to find out what is the total adsorption mathematically became an impossible task. So what they further made assumption, in second layer and higher number of layers, these energies are all same and they equal energy of liquefaction. Okay, now how does this thing gel together? Because energy of adsorption is indication of how much force, how strong the force of attraction is between the surface and molecule. Okay, E minus EL. This is EL is energy of liquefaction. This basically, this difference tells you whether the gas molecules are attracted more towards the surface or whether they are attracted towards each other. Because if they are attracted towards each other more than the surface, then the gas is likely to liquefy rather than adsorb. Okay? And if I go back, number 3 and number 5, they are indicative of situations where the attraction between adsorptive molecule or the gas molecule is more than the attraction between gas and the solid. And that's why you don't see you don't see a hump like this in these cases. In these two cases, you don't see a hump like this, which also means if you have got these type of isotherm in your measurement, you cannot calculate surface areas from there. Okay? Because there doesn't seem to be formation of a monolayer at all. You can't calculate surface area. What you should do, if at all you get isotherms like this, you should try and change the gas. You can't change the material. You should try and change the gas. Maybe on some other gas, it does give you a nice isotherm. Okay? A typical type 1b isotherm, and it's an activated carbon. Sorry about that. Just wanted to show you something. Surface area calculations using the BET gives you this. Okay. You can see the points that are used for calculation is starting from 0.01 and ending at about 0.09. Now, the normal recommendations, if you talk to classical people or read classical books, is that BET will be applicable between 0.05 and 0.3, in between those partial pressures. That's not a Bible as far as gas adsorption is concerned. It doesn't apply to all situations. In this situation, BET is applicable in a very low pressure range. Rest of the things, if you look at, slope is nice, y-intercept is positive, C is 754. Now, another point of consideration now is, because if you look at BET's original paper, they said C should not be more than 300. It should be between about 10 or 300. But under the new guidelines from IUPAC, you can consider C values, higher C values as well, so long as some other conditions are right. Other conditions are, all should be positive. C should be positive, Y should be positive. Slope is anyway always positive. The experiment is done rightly. Correlation coefficient is the measure of the straight line. Okay. Measure of this straight line. How straight this line is. It should be at least 498 or 49, let's say 7, that should be the limit. Ideally 59, 99.999. Here in this case, it is 99997, which is okay. It's a nice straight line. Very important point they discuss is that what you see as QM is the quantity in the monolayer, means volume in the monolayer. This should be part of the calculations that you are part of the table that you are taking for calculations. So these are the pressure points we have taken for BET calculations. The quantity adsorbed at these pressures are this. This 240 should be somewhere in here. Okay? It should not happen that you are considering these points and trying to evaluate something which is here. Okay? So this monolayer that you are trying to determine or trying to calculate should be somewhere in the point that you have considered for calculations. It should not happen that quantity adsorbed in monolayer should not be outside the range that you are considering for BET. That's a very important conditions on them. We also applied Langmuir here. And I think this slide was, if you read my earlier narrations, I would have said that this is not an appropriate BET calculation. I would have said that. The reason for that would have been C value. Because C value is much higher than what BET thought it should be. I would have told you this is not a correct surface area calculations. And the correct one at that time would have been this. Okay? But remember, this is Langmuir equation applied there. Remember, by the way, Langmuir does not need saturation pressure. Langmuir equation always has the absolute pressure in calculation. The only problem here, which was not there at that time, here is that your QM or the volume in the monolayer is 285 and you don't have 285 here. Okay? And that is why I think the BET calculation remains acceptable. This is the one which is acceptable. Another example which shows you a negative C value and negative y-intercept. I don't know whether you can really see it, but negative y-intercept, negative C values. Negative C values is the same thing that I told you. EL is, E1 is less than EL, which means there is more attraction between the fluid molecules rather than the solid. C being negative has no physical significance, and that's why we cannot consider that. Similarly, y-intercept being negative also has no physical significance. So whenever you apply BET equation, in this case, the pressure table that has been chosen is 0.06 to 0.3, which is the regular recommended pressure range for BET. And we get absolute values for surface area. We change the pressures. And now we reject the higher pressures and we select some more pressure from lower range. So this one is 0.009 to 0.1. And you get C value which is positive, y-intercept is also positive. It's a very nice equation. And therefore, QM is 8.5, which is part of this. So it's a valid BET calculations. Only thing is the range of application is different from the normally recommended range. So when you are applying BET, please look at the range you are selecting. And if you don't get the conditions right, you should change them. Langmuir. Here also, although the equation, It's only 9998. QM is also outside the range, and I believe we shouldn't take that for calculations. No matter what you publish, for God's sake, write, if it is a BET equation, along with the C values. I don't know how many of you follow while publishing or while publishing papers, how many of you follow guidelines? But IUPAC mentions some guidelines for publications. And the value of C, the pressure range, is some of the things that they ask you to mention when you are publishing BET values. Don't say my surface area of my sample is so-so. The problem why all of you are spending time here is very basic problem in analytical chemistry or the experiment that you do. If a group consists of about 5 or 6 people, ask any two to match their results on the same material for the same experiment. I doubt if you can do that. And the reason is that you don't follow a set procedure for doing an experiment. So there is a lot of repetitive work. Whatever you do, nobody expects you to do a very wide range of work for your, let's say, PhD or this thing. Even if you are limiting to certain materials, only 2 or 3 of them, try and do a conclusive work. If you do a conclusive work, the third person or fourth person who joins your group knows that, okay, this is what I don't have to repeat. I will work on a different material. At least that much time can be saved. I mean, it's not just one of the this thing, but conclusive research is something one should be aiming at. In whatever you do, just one experiment. After all, one PhD, how many samples do you analyze? 5, 10, not more than that. Maybe you're doing about 6 or 7 types of experiments on them. Try and be conclusive about what you are doing. And this is one of the requirements to be conclusive. This is at least 4.9. It should be greater than 4.9, means 4.97, 4.6 to 8.9 is okay. Y-intercept positive. C value, I've kept a question mark there. In earlier slide, it used to be 300. Between 10 and 300, I think higher values are acceptable now. Okay. Take about half a minute rest if you want to. We'll move on to the mesoporous evaluation, the mesopores evaluation. Let me see what half a minute recess means for you. If you have any questions, you can ask. Beg your pardon? Yes. Well, you have a mic for them to. I want others also to listen to your question. The session is going to be slightly longer because I think, where is Professor Chenna? Kesavadu. He asked me to take part of the particle size analysis also. Okay. So following this, I will do that. I will have this short recess every after a particular session.
Earphones, Vara.
Okay. It is.
What I wanted to know about the type 3 isotherm, as you said, like the type 3 isotherm is forming when there is no monolayer formation, right? So it's because of our material, the problem with our material, or
It's not just the material, it's a combination. Material and the gas. Okay. Now,
then how can you know that like
how can I know that it is what?
whether the problem is- So,
I said both. I'll explain, don't worry. Adsorption is a function of nature of the solid as well as nature of the gas. Okay. Certain solids and gas combinations will give you that. But since solid is the material that you want to study, I won't ask you to change the solid. The gas is something that you can change. Use a different gas. Could be argon, could be carbon dioxide, could be water vapors, could be anything. Frankly, I can't hear you. I mean, I'm old. That is for sure. But yeah, it's okay. 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 Helium is not an adsorptive. Helium is not the gas which is being adsorbed. Helium is used because it cannot be adsorbed. Helium is used to calculate, to find out free spaces. And free spaces are defined by space outside the material. So helium should not be adsorbed. That's why helium is chosen. Helium is not the gas for adsorption. Argon and nitrogen, yes, one has a merit, one has slightly more merit than other one. Basic criteria to choose nitrogen for most of the time is it's easily available, it's much less expensive, okay, and it gives. There are many modeling that has taken care that is done considering nitrogen gas, so nitrogen can be used. In some cases, argon becomes slightly more preferable for different reasons. Very rare situations. I can name only about graphite with argon. It shows you that it shows you two things. Number one, the surface is very, very uniform as far as energy of adsorption is concerned, which is what the original assumption was, but is not true in most of the material. In this case, it is true. Okay. So first thing is that the surface is very uniform as far as energies of attractions, adsorptions are concerned. Second thing is it also shows that the van der Waals forces are really a long range forces. Okay, so you get steps.
Okay, sir. Thank you, sir.
Okay.
So myself, Prasanna. How can we use BET calculations in organic molecules?
Although you have a mic, speak a bit louder.
How we can use BET calculations in organic molecules?
How do we?
Use BET calculations
Huh?
in organic molecules.
How does it matter?
Like
What is the procedure for BET calculation for an organic molecule?
Organic molecules.
yeah.
Let it be organic molecules. I don't think we have said, I have said anything that differentiates the type of the surfaces or the type of the materials. What do you think could be the problem?
Sir, I'm not getting your point. My point is, how do we calculate the BET on organic molecules? There any use for organic molecules?
You
in order
say,
to
is there any use of organic molecules being studied for
BET calculation?
BET calculations?
Yeah.
Ask any of the pharmaceutical people. They die to measure surface area for their molecules. And many of them are organic molecules. Okay. Surface areas are studied because it tells you the activity of your surface. Okay. These activities are manifested in many forms. For example, how nicely it can be packed. The organic molecules, if you want to make a tablet out of them, how nicely can they be packed? How nicely will they flow? If you are pouring one material from one to another place, how nicely will that flow take place? So BET has a use, surface area has a use for organic molecules without a doubt. Is that your question?
Yes, sir.
So organic, whether it's organic molecules or inorganic molecules, it doesn't matter. They are studied for surface areas because surface area is a very useful study to know how active your surfaces are, both physically as well as chemically.
But currently in my research work, I am not carrying that BET calculation. So I ask.
No, if you are supposed to do that, please do it. If your guide doesn't ask you to do that, don't do it.
My guide is supportive, sir.
Huh?
My guide is supportive.
Then
So I'm asked that.
you are all the support, you have all the support in the world. You don't require anybody else's support, so long as your PhD is concerned. But anyway, see, what is the topic of your research, may I ask? If it is not a secret.
No, sir, it's not like that.
Then?
Synthesis and characterization of heteromolecules based on their biological activity or else energy materials.
For pharmaceutical research?
Yes, sir, organic chemistry pure.
Okay, you finish your PhD, when your material comes out, then pharmaceutical company will require this surface area measurement. I can assure you that. Okay?
Okay, sir.
You can do whatever your guide says, but obviously when the material comes out and is being used for your any formulation that comes out of what you're doing, its activity inside your body is a function of surface area of the chemicals that go inside, okay, in some form or the other. So at some point of time, you might require to measure surface area of the formulation that you develop. That is for sure. But about 80% or 90% pharmaceutical companies use surface area calculation. Okay?
Yes.
It's there in the pharmacopoeia. Is that answered?
Yes, sir. Yeah.
Huh. For the time being, don't bother about it. Okay. Yes. But it is useful at some time. I said it is in the pharmacopoeia. So you will have a use for it.
In pharmacokinetics and dynamics is there, sir. We will, how the drug is absorbed, we will see.
How that drug
Drug is absorbed to the human body,
yes.
but we can't see the surface of that drug. Like that, my question. There will be a absorption, metabolism, ADME parameters.
You need that drug formulation in the form of, I don't know how you are taking it. Nobody is taking it as a powder most of the time. How does that drug dissolve or what you call dissolution test? Do you do dissolution? Are you aware of dissolution test? No?
No.
So you are working only on the molecules as of now. This dissolution test is an important test in drugs, in pharmaceutical. And that dissolution test, the basis of dissolution test is the surface area or the material that go into form that tablet. Okay? It is important.
Thank you, sir. Got it.
And you're not very wrong. I think the first surface areas instrument, at least in the country, was sold in about 1995. Before that, no surface area measurement was being done. The first particle size analyzer to a pharmaceutical company was sold in about 91, 92. So nowadays, nobody asks the question, why is particle size being measured on pharmaceutical samples? The first one was sold in 91 or 92. Before that, drugs were being consumed, tablets were being consumed. But this started only later. Okay? Huh? Malvin did a very, very hard work on pharmacopoeia. And I think, yes, Malvin got the most of the rewards of that hard work. Marble is very, very successful in pharmaceutical market. Apart from my introduction, I'm not really talking about the brands or the models. Okay. Type 4A and type 4B. We are talking about these samples. This region here in between, this is the multi-layer region from where we try to calculate surface areas. At low pressures, very, very low pressures like this, the information about micropores are contained, if at all they are there. So if this sample has micropores, we will have to study this region also. But for surface area, we studied this region. And now we are talking about mesopores or larger pores, for which we are studying this region. Okay? It is okay. I think battery is gone.
Hello.
Let me see how the coordination is between left and right of mine. Hello. It's okay? Okay. See, these are the pores. Okay. When you started adsorption, even the surface inside the pores were being covered by the gas molecules, like they were covering the entire surface. Even the surfaces inside were being covered by gas molecules. That's why you see this layer inside the molecules. Now, what happens is, for a given pore size, there comes, and you know, you are continuously raising the pressure. So more and more gas molecules come and adsorb on the inside surfaces. There comes a pressure at which, for a given size of pore, see, this is a larger pore than this. For a given size of pore, Q2, and that's a technical term, I'll spend the whole afternoon explaining it. Q2, what is known as gas liquid transformation. In this region, this is gas, and what is going to happen is, because of the curvature effect, due to gas liquid transformation, the oncoming molecules that come nearer this pore condenses into a liquid. Now, you can say that in more than one way. You can say that the saturation pressure is reduced. And when the saturation pressure is equal to the pressure, it liquefies. One way of saying that is this. The true reason is that gas liquid transformation causes the gas molecules to condense in a confined space. Okay, that situation is hard to visualize because you have this gas adsorption thickness, and in between, in the core region, you have liquid. And liquid, like any other liquid in a cylindrical vessel, you will see a meniscus forming. Okay. Gas adsorption and then liquid condensation, or gas condensation, which is the liquid form. That is why I said gas liquid transformation. This transformation causes the gases to condense, or you can see the saturation pressure to drop. Okay. And to what level will it drop? At the pressure that we are considering. I said for a given pressure, for a given cycle of pore. For that pore, your P0 will reduce. Gas condenses. This was studied by Calvin. Calvin happens to be my guru's name in micromagnetics, that's why Calvin. Calvin gave us an equation. This is all modeling. I'm not taking the names of the. Calvin gave us an equation which related radius of the core to the pressure at which condensation will take place. Okay? If I go back, the radius, sorry. How do I go to the? Can you see that? No, I want it in the slide. Yeah. Kelvin related this radius to the pressure. At this pressure, this size of the radius will fill with the pore. Okay, we'll have the condensation. So what we now have, if we apply Kelvin equation, we can find the radius of this pore liquid, meaning the radius of the meniscus. That is not the pore size. The pore size actually is RK, which is the core radius, plus the thickness of the layer that was pre-adsorbed before this condensation took place. And since it is happening on both sides of the wall, the factor of 2. Now, if you want to calculate from the gas adsorption isotherm, if you want to calculate your pore size, what you need to do is apply Kelvin equation so that you get RK, and then try and find another equation which will relate T to pressure. So both RK and T will be related to pressure, and since pressure is already there, you can find out the total diameter of the pore which is being filled at a given pressure. This thickness T is known as statistical thickness. Okay. There are various equations, there are ways to make T or make your own T plot, means make your own relationship between pressure and T. But the ones which are available already work very well many times, and these are these things. You have Harkins and Jura, you have Halsey, you have Brookhoff de Boer. These are the equations available to you already. Most of the commercial instruments will have those things. So just select a particular equation. Remember, T is being related to P by P0 here, both the equations. You can finally find out at this pressure, this is the size of the pore which is being filled. And since you are already measuring the volume at every pressure, you will know which size of the pore has how much volume adsorbed. Now these two columns will give you pore size distribution, volume pore size distribution of your material. Typical few things I want you to see, or maybe when I talk about other models, I'll tell you. If you are having these slides with you later on, there are explanations for these desorption curves and shapes. Okay, here also, two new shapes have been added, like they were added into the isotherms. These shapes have also been added to the hysteresis loops. The following slides will tell you the explanations. Let me jump to microporosity, but without with certain caveat to whatever we have done so far. This T plots, that equation that you saw, is an important part of the pore size distribution. Okay. Now, T plots are classically made by studying adsorption on a non-porous material of similar chemical nature, but non-porous materials. Okay. Obviously, there is basic flaw in that. The basic flaw is that none of these T plots take into account the curvature of your pore. Okay. And that's a huge effect. With the result, what they found out is when they studied, see what happened in olden days, there were no materials which could be considered as model materials. For example, there were no materials with a very clearly defined pore sizes without any net working of the pores. But today you have those materials, which means that you can do experiments, calculate their pore sizes, and then try and match them with the, let's say you can study these materials with the microscopes and then match the results. What they really found, but that should not deter you from doing those exercises. What they found that BGH calculations, the pore size calculations that we were studying so far, underestimated the pores. Okay. And the reason was the T plot being used. It was not the Kelvin equation. Kelvin equation posed different kind of limits, but basic calculation had this T plot, which was a problem. So what IUPAC now recommends is that by all means BGH can use it, provided you mention that it is the pore size that you are publishing is using BGH calculation. That's more important. But they think that using some of the modern theories which are based on molecular dynamics, like your GCMC grand canonical Monte Carlo calculations, or what is known as DFT, density functional theories. These two will allow you to calculate both micropores as well as macropores. Okay, and are thus most preferred way of doing pore size distribution in both the regions. Let me carry you through to micropores, which is towards the last of this. Their modelings are Harwood-Cavazo. Again, relationship is between pressure and diameter of the pore. Originally was meant for slit-shaped pores, which are famous in carbons. There were modification to Harwood-Cavazo by these gentlemen, Saito Fole, allowing you to calculate cylindrical pore shapes. When you are talking about micropores, the pore shapes are very important. Different type of the pores will adsorb to different extents. And that's why anything that you are studying now will be pore shape specific. Okay. In Cheng and Yang for spherical pores, same thing for spherical pores. I'm not going into the equations. You also don't go into the equation if you want to save yourself. Oh my God. I'm not a very techno-savvy guy. I don't know how to do this presentation on. I couldn't write this equation. Okay. But I like this equation so much that I hand wrote. We are now talking about density function theories. Okay. What happens is you can model your adsorption in micropores using whatever methods. Okay. Now, obviously, one that is more valid will find more fame and probably more money to the inventors. But density functional theory and similarly Monte Carlo statistical calculations allowed you to model your adsorption keeping in mind the nature of the solid, the gas, the shape of the pore, and the temperature of adsorption. Now, all these four things are very important. So let's say you are measuring some material, you're using some material. Did your measurement of gas adsorption did your measurement on gas adsorption? Now you want to find out its pore sizes. So you have done your experiment on a particular solid type, using a particular gas at a particular temperature. You have some idea about the pore shape also. What these modeling does is they allow you to theoretically calculate the isotherms given these four conditions: solid, gas, shape, and temperature. You are allowed, you can make theoretical isotherms. The one here is a theoretical isotherm of a given pore size. If this is the pore size, then your isotherm is like this for argon on a slit pore. I don't know the material here. That's not mentioned. Now, for this pore size, it is this one. Again, different. You change the pore size, have another one. Change the pore size, have another one. What you will ultimately have is this type of things: different pore sizes, different isotherms. These are theoretical isotherms known as kernel. The software will have lot of such kernels already stored. Okay. Your experimental isotherm is this one. Now go back to this equation. What is this? This is known as the general adsorption equation. Left hand side is your isotherm, which you measured. Okay. On right hand side, there are two parts. NP by P0 for a particular W, which means pore size. Theoretical isotherm. Okay. FW is your pore size distribution function. And it's integrated from minimum pore size to the maximum pore size. W max and W minimum. This is W minimum. This is how it is written. Okay. How do they do it? This exercise will also be useful for particle sizing. Take now. What they do is, they choose a particular kernel. Okay, this is your experimental isotherm. Ideally speaking, they have to find out how many of which pore sizes should be combined to give you a combined effect of this. Okay, like deconvolution, it's a deconvolution. Your experimental isotherm is a convoluted isotherm, contains a lot of pores. In order to separate all of them and find out how much is the contribution from each size of the pore, that exercise is known as deconvolution. What they do is they assume a certain pore size distribution from here, compare it with this, again go back, change this, again go back. It's an iterative process. And take only a few seconds to give you the exact pore sizes which will most accurately be represented by this isotherm. Obviously, once you want to do deconvolution, you don't cover 100% of the curve. So there will be some loss of fitness, and that figure is indicative of how well your model has applied there. That figure is available to you. Mostly works very well, very, very well. Okay. These are some of the slides. For isotherm, you have Langmuir, Temkin, and Freundlich. For surface areas, BET and Langmuir. For pore size, classical theories are this. I have added mercury porosimetry also there. And of course, the DFT that we talked about. Thank you. As far as gas absorption is concerned, it's slightly longer. But you guys don't want it. How many of you are using particle sizing? Likely more than what you're using. All of you are using laser scattering methods or some other methods? Who said no? Somebody said no. Don't look at the back, the ladies voice. All of you are using laser sketching methods for particle sizing? You said you are using particle sizing. When I asked you which method you are not light scattering? All of you? Okay, we will stop in one minute. Just give me 2 minutes. Up. And I promise I won't take more than half an hour.
More participants to have a break of around 10 to 15 minutes. Thank you.
Outside, sir. Server outside, sir. Break time. Sir, stay confirm organizers. No back, no We have.
Should we start? Perfect. So good morning, one and all. At the outset, I take this wonderful opportunity to thank the organizing committee members for inviting Thermo Fisher Scientific to be part of this event. It's an absolute honor and privilege to be with you all. So ladies and gentlemen, my name is Karthik Balasubramanian. I work as a senior product manager with Thermo Fisher Scientific. And over the next 45 to 50 minutes, we are going to see about some of the basics and introduction to X-ray photoelectron spectroscopy. And following this lecture, we will also have another lecture on data interpretation, where my colleague, Mr. Ratul Paul, will join you all through online. So with that sort of a brief introduction, let me get started with my presentation. So ladies and gentlemen, with the advent of advanced and functional materials over the last 10 to 15 years, we have seen ever-growing plethora of new materials. We have seen new combinations of materials, and every material that we see in the recent age. One interesting aspect that has come is the surface has started playing a very critical role. The surface is the point where it interacts with the external environment, or it is the point where it interacts with the other layered material. So the surface has started playing a very, very important role, particularly in the last 15 to 20 years. And when we talk about characterizing the surface, there is no other technique which can give you the wealth of information that an X-ray photoelectron spectroscopy can do. And in this presentation, I intend to give a basic introduction and theory into this exciting technique of X-ray photoelectron spectroscopy. But before I get into it, we represent Thermo Fisher Scientific, and we are absolutely proud in our mission. We take pride in our mission that we enable customers to make the world healthier, cleaner, and safer. So gentlemen and ladies, we were talking about X-ray photoelectron spectroscopy and the importance of surface. And as we talk about characterizing the surface, every material or an industry, every industry that we take, irrespective of either it is a petrochemical industry or the solar industry, the semiconductor industry, or even the thin film industry, you name any industry, irrespective of the materials these industries work on, the surface plays an absolutely important role, because surface is the point or the layer where it defines the property of the material. It could be any property, either it can be the adhesion, the contamination, the corrosion, the thickness, you name the property, it all lies on the surface. So if you want to get a complete understanding of your material, if you want to have a better understanding of the material that you are working on, characterizing the surface becomes absolutely important. And that's where XPS plays a very, very important role in the range of analytical techniques that we have today. But as I keep repeating the term surface to make it common for the audience, what do I mean by a surface? As I keep repeating it again, any sample that you take, either it can be a bulk or it can be a powder, it can be a fiber. Any sample that you take, the sample can be divided into different layers depending upon the depth thickness. And when you look into this schematic, the layer that is marked in red, that corresponds to roughly 3 atomic layers, and that's 1 nanometers. In true sense of surface characterization, this is the layer, what we call it as a surface, the top 1 nanometer. And the next layer that comes in, that corresponds to 1 to 10 nanometers, roughly 3 atomic layers, and this is called as ultra thin film, the one that is marked in blue. And whenever we talk about XPS, any information that you get out of an XPS comes from the top two layers, which is the surface and the ultra thin film, and that corresponds to roughly 10 nanometers on the surface. That's where you have all the information that comes from XPS. And the rest of the layer is called as a thin film and now the bulk. Now, one interesting aspect that the audience should embark here is that we have many techniques which give us very useful information. One key difference between XPS and all the other techniques is that all these other techniques which give us very useful information, most of them give you information from the bulk of your material, which is roughly few hundreds of nanometers to few hundreds of micrometers. And the information comes from the bulk of your sample. Either it can be the EDS, the XRF, or the XRD. But one difference is that the XPS gives you information from the absolute surface, which is top 10 nanometers. And with that, considering we have a larger audience coming from the research community and the student community, let me take a couple of minutes to introduce what is the theory behind XPS. X-ray photoelectron spectroscopy works on the principles of photoelectric effect, which was discovered by Einstein in the year 1905. He was the first one who brought out the phenomenon of a photoelectric effect where photons are ejected from the surface of a sample. And based on this principle, we had a Swedish scientist called Dr. Seibach. Seibach in 1960 built an instrument based on the photoelectric effect, which in those days it was called as an ESCA. And for this instrumentation discovery, Seibach was awarded the Nobel Prize. So this instrument has been in existence since 1960s, and particularly from 2000, it has become very demanding and popular and has become one of the important characterization techniques in an analytical instrumentation. So what happens in XPS is that we have a material, and we all acknowledge that material constitutes of atoms. And in an atom, you have the nuclei in the center. And we have electrons which are revolving the nuclei in certain fixed orbitals. The number of electrons in orbitals, that depends upon the atomic number of the element that we are looking in. So now in an XPS, what we do is we take an X-ray of known energy, we shine it on the sample, and this X-ray, as it comes and interacts with the sample, it imparts its energy and momentum on the electrons that are revolving in the orbitals. And this shift of energy and momentum is quite sufficient to knock this electron out of this orbital. Now, this electron, which is knocked out, is called as a photoelectron. Now, using the XPS analyzer, we collect all these photoelectrons which are ejected out of your sample. Now, the mathematics gets interesting. You know the energy of the X-rays, what you are using. You have measured the photoelectrons, the kinetic energy of the photoelectrons which you have collected. And using these two measurements, in turn, you calculate the binding energy of this photoelectron. Now, why does this calculation of binding energy become so interesting? Because when you know the binding energy of this photoelectron, it can exactly tell you from which element this photoelectron was ejected and from which orbital this electron was ejected. And more importantly, when this electron was ejected, what was the chemical state of the element? All these three information to come from the surface of the sample, top 10 nanometers, XPS is the only available technique which can give you that information. And when it comes to XPS, we normally do two kinds of a scan to get better understanding of the sample. The first scan, which we call it as a survey scan or a white scan, it scans the element over a larger binding energy range, and that gives you a picture of what all is present on the sample surface. XPS is not a technique which is used to only identify the elements that is present. It is also a quantification technique. It can tell you what is present and how much is present. This information, you get it from the survey scan. And once you have done a survey scan, you identify the region where you are interested in, that you want to explore more. You run a second set of survey scans, which is called as an high resolution scan. This high resolution scan clearly tells you the chemical states of the element, what you're trying to look at it. So here is an example of two chemical states of polymer, the spin cast and the sheet polymer, which clearly tells you the chemical state of the polymers that you are looking in. So on an XPS, we always do two kinds of a scan. One is a survey scan, and the second one is a high resolution scan to get the chemical state. Now, the beauty of XPS is that when you work on an element, XPS is a technique which can clearly tell you the difference in the chemical states of the element that you're looking on. For example, if you're working on iron, iron can be in different states. Either it can be as a pure iron, or it can be as an iron oxide, or it can be as an Fe2O3. The spectra, what you get out of an XPS, will clearly tell you the chemical states of the element depending upon the binding energy, which can be fingerprinted against the XPS atlas to understand what is the chemical state of the element that you are looking at. So few examples of polyethylene, polyvinyl fluoride, and PTFE, which shows the different chemical states of the element that you're looking on. Now, this XPS has progressed tremendously over the last 10 to 15 years, because previously one big challenge that remained in XPS is that in order to do an analysis, you need samples which were good conductors. If you had non-conducting samples or insulators, then you would have a charge buildup on the surface and you would not be able to collect any good spectra. But all the modern day instruments, they have a fantastic charge neutralization technique that helps you to neutralize the charge buildup and collect a very good spectra even on surfaces like glass, quartz, or wood. So the conductivity nature of the sample has been taken out of the equation completely. So how does XPS compare with other techniques? In a modern lab, we have many analytical techniques which we are going through in this 3-day event. All these techniques, they give a very useful information which helps our understanding of the sample to get better and better. There are no techniques which can replace one or another. The information from all these techniques, they are complementary to each other. That's an important aspect we should accept. But when it comes to an XPS and surface analysis, when you're keen on doing a surface analysis, XPS has little bit more advantages, or is the only technique which can fulfill all the criteria of a surface analysis. When you go to other techniques, which are down here in the list, they all give you very useful information. But when it comes to surface analysis, XPS is the one technique which can fulfill all the requirements of characterization. So just to quickly summarize what we have seen so far in the last 10 to 15 minutes, XPS is a technique that works on photoelectric effect. you have an X-ray of known energy which shines on the sample. The X-rays come and knock on these electrons, and these electrons are ejected out of these orbitals. These electrons which are ejected, these are called photoelectrons, and these photoelectrons are collected by the XPS analyzer, which helps us to understand what is the binding energy of the photoelectron. And the binding energy helps you to understand what element it is, how much it is, and what is the chemical state of the element. And usually on an XPS, we do a void scan to understand all those materials which are present, and a high resolution scan to understand the fine structure or chemistry of the sample. So now getting into the second half of our talk, this is more sort of focused towards the instrument that you have in your Center for Advanced Studies, the K-alpha XPS. So this K-alpha XPS has been one of the super hit models that has come out of Thermo Fisher Scientific. The reason I say it as a super hit model, it's because it not only enables you to analyze all different kinds of a sample, but it also brought in an aspect of automation into XPS analysis. The previous generation instruments which were available, it required a tremendous amount of expertise and skill from the operator who is running the instrument. But this is one model which broke all the barriers, brought in automation into the operation, and that made XPS analysis easy and feasible for every single user. So the presentation will go forward, taking some of the aspects of this instrument into the picture, and this will be demonstrated as well in the following lecture on XPS. And when we talk about K-alpha, some of the basic characterization requirements on XPS, like the point analysis, the imaging, or the depth profiling, all this can be done in an automated way on a K-alpha instrument. So what we have in a K-alpha is that this is a picture of the instrument which we will see. This is where we have the analyzer and the X-ray source. This is the load lock where your sample gets into the instrument. You have different setup of cameras which help you to get more and better view of the sample. And then you have a box which encloses the whole instrument. Now, when it comes to an XPS, I mentioned a few minutes back that this K-alpha instrument was a path breaker when it comes to handling the instrument. Here you see an operator loading a sample box, sample tray, which has about 25 to 30 samples. This was not a picture that was possible before. Now here, what this operator does it, she opens the load lock, places the load lock tray here, closes the load lock, and lets the instrument automatically pump it. And once the load lock reaches a base pressure, this system gets automatically transferred to the analysis chamber automatically. What I meant here is that you load your samples here, and once the vacuum is reached, there is an arrangement which automatically transfers the sample from here into the analysis chamber. And this is a big breakthrough, because the time when I was doing research a few years ago, you had to manually transfer the sample. You load your sample into the load lock, wait for the base pressure to build up, then you have to physically insert the sample from the load lock to the analysis chamber. The problem there is, if you don't have steady hands of transferring the transfer rod, there is a greater danger that you crash the vacuum and you will not be able to operate the instrument for the next 2 days. And this was a big jump over in terms of sample handling and sample transfer. And when we talk about this sample handling, one critical factor is the UHV system, the ultra high vacuum system. Why do we need an ultra high vacuum? Please remember, on an XPS, we are collecting photoelectrons and we are measuring the binding energy of these photoelectrons. So it's absolutely essential that you collect the photoelectrons without changing the energy with which it is traveling from the sample. And for that, you need a system which has no gas molecules to interact with the photoelectrons. That's where you need an ultra high vacuum system as part of the system buildup. And to achieve ultra high vacuum system, most of the modern day instruments, they have complete oil-free pumping system. Oil-free pumping system, it's not only the fact that they give you less noise during operation, more importantly, they leave you less contamination. They are far more efficient to pump faster. And that's the reason most of the instruments on the XPS, these are oil-free pumps. So in this case, you have dedicated turbomolecular pumps backed by scroll pumps. Now, when we talk about ultra high vacuum, now here is one constraint that comes from sample handling. XPS is a technique which works on complete ultra high vacuum. So when you're talking about ultra high vacuum, then the possibility of having samples which are biological samples or have water content in them, that is not possible on an XPS. Because the moment you have a moisture or water content on your sample, it will start degassing and it will disturb the vacuum internally on the system. And this applies not only to the K alpha instrument that I'm talking about, but overall every single XPS that operates on an ultra high vacuum. So typically to talk about these instruments, when I say UHV vacuum, they are in the order of 10 to the power minus 9 to 10 to the power minus 10 millibar. So moving forward, we looked into the basics of XPS and we looked into the importance of a vacuum. So when you look into an XPS instrument, not only the instrument here, but any other institute that you see at XPS, we always wonder, what does this instrumentation have inside? Because when you start your research career, it's very, very important that you start also understanding the instrumentation part, so you'll be able to acknowledge and appreciate the engineering aspect that has gone behind the instruments that give you very useful information. Now, on an XPS, a schematic will show you that these are the critical equipments, the main parts of any XPS system that you will see here. It might look very complicated from outside, but if you break down into small halves, it gets our understanding very important. So now where do we start here? To start, the first thing, if you recall, on an XPS, you are going to shine an X-ray of known energy on the sample. So how do I get an X-ray? It starts from the point here. Here, you have a thermionic emission. A thermionic emission is something which can be either a tungsten or a lanthanum hexaborate called as LAP6. You can use these filaments, and when you start heating these filaments at a certain temperature, when the temperature overcomes the work function of the material, these emitters, they start emitting electrons. And these electrons, they are fine focused, so they go and hit an aluminum target. An aluminum target is nothing but like a 10 rupee coin. A 10 rupee coin aluminum target is kept here. And as these electrons strike on the aluminum target, you get X-rays which come out. You get aluminum K alpha X-rays which come out of this target. Now, the point to be noted here is that you get X-rays out of this target, but the X-rays which come out here, they are not of uniform energy. there is a small delta E variation in energy of the X-rays that come out. But if you recall our mathematical equation, the energy of the X-rays plays a very important role and it has to be a constant number. So how do I achieve that number? So these X-rays are made to pass through a monocrystal. A monocrystal is nothing but a Bragg crystal, which is arranged in a certain way that X-rays of a single, X-rays of different energy enter this crystal, and energy of one single X-ray can come outside this crystal. That's what a monocrystal, Bragg crystal is like. On a TM, we call it as something similar, monochromator. Here it is called as a monocrystal. So these X-rays, which enter this monocrystal of different energies, come out with a single energy, which is 1486 eV. So as these X-rays go and hit on your sample, you have photoelectrons which come out of the sample. And these photoelectrons, as they come out, along with the ultra high vacuum and the biasing of these electrostatic lenses, these photoelectrons are pulled towards the analyzer. It goes towards the analyzer, and the analyzer helps to split the photoelectrons based on different binding energies. So you collect electrons on the detector on different binding energy scales. So apart from these specific topics, you will find there are two more guns which you locate, which is a flood gun and the ion gun. If you recall, in one of the slides I mentioned that even if you have insulators, modern day instruments can do a charge compensation and you're still able to analyze them. And the role of a flood gun is to help charge neutralization on your sample surface, either for conductive, semiconductive, or insulating materials. The second one here, the ion gun. If you recall again, I mentioned that XPS is a technique which gives information only from the top 10 nanometers. Many times you need information beneath 10 nanometers as well, because that's where your science lies. So in those cases, this ion gun uses normally argon ions of a certain energy, helps you to mill the sample. It helps or sputters out sample in a controlled fashion. So you can start doing XPS analysis below 10 nanometers. And that's the reason you have an ion gun. Apart from that, you have certain cameras which help you to get different views of the sample that you're trying to work on. So that's a quick overview of an XPS instrument, what we are talking about. The key point here is any XPS, irrespective of the model or the brand that you go on seeing, as a student community, it's very important you acknowledge the different parts of an instrument. So you are able to appreciate the build of the instrument as you work for your research. Yeah. Yes. So the monochromator, the function of this monochromator is to give you X-rays of a single energy, 1486 eV. And as these X-rays come out of the monochromator with a single energy 1486 eV, it goes and scans on your sample. As it scans, you get photoelectrons, and these photoelectrons, they travel with a certain kinetic energy. So we are collecting photoelectrons, measuring the kinetic energy, and in turn, we are calculating the binding energy. It's only the binding energy which tells us what element and the chemistry of the electron. Did I address your queries? Thank you. So going forward, how do we handle samples of different nature? Because when it comes to XPS, you should always remember it's a surface characterization technique. Many of the times what we observe is that people do have a feeling that if they put in more and more samples, there is a possibility of getting better information, which is not the case. Because irrespective of the amount of the sample that you use, it's only the top 10 nanometers, the cleanliness of the top 10 nanometers that matters in an XPS. So in order to facilitate different kinds of a sample, we do have provided certain standard sample holders, which has to be chosen depending upon your sample handling requirement. So this is a universal holder. This universal holder can be sort of used for every bulk sample that has a certain fixed geometry. When you have a certain good sample with a fixed geometry, you use a double-sided carbon tape and you can stick those samples, and ideally you can use 4 samples in each slots and you can get up to 36 samples in one go. When you have different kinds of a sample, not necessarily in a good geometrical shape, for example, you might have powder samples. Most of us work with powder samples. When you have a powder sample, and if you go for this universal holder, if you stick 2 samples nearby, the moment you insert it and the vacuum starts pumping, there is always a chance of cross-contamination. So in order to avoid cross-contamination, whenever you work on powder samples, you need to use this holder dedicated for powder samples. This powder sample holder has 9 depth holders, which help you to load powders of very small quantity. The great important aspect is that it eliminates the possibility of cross-contamination. Likewise, there are many of us who work with electrospun fibers. When you want to do a characterization of fibers, there is a dedicated holder for fiber handling. Now, what is the problem when you mount a fiber sample on these kind of holders? Normally, these holders take a double-sided carbon tape, and when you put your fiber on a double-sided carbon tape, you will have more of carbon background, which you will see in the spectrum. So if you want to avoid that background, it's always recommended that you go for the fiber sample holder. And the last one I like to discuss is that I mentioned about a technique which is called depth profiling. So when you are doing a depth profiling experiment, if you keep your sample stand still and start milling the sample, the finish or the slice of the edges of your sample may not be neat perfect. There are possibilities where it can leave a curtaining effect. So in order to avoid that curtaining effect, as you start removing the material from your sample, it is also advised that the sample keeps rotating so you have a clean finish, particularly on the edges. So these are the standard holders which are available with the facility what we have, and it is strongly recommended that you utilize all these holders depending upon the type of your sample nature. And there are many of us who also work with thin films. When you work with thin films, normally the expectation is you want to understand what is the depth thickness of each layer on an XPS. So for those kind of experiments, you have a module called tilt module, which helps you to do angled resolved XPS. So when you have multiple layers, you can load samples on this. The advantage of this module is that it can tilt from plus 90 degrees to minus 90 degrees. So the advantage for a user is that you can tilt your sample at certain tilt angles. So you can make the X-rays to hit on your sample at a glancing angle. So depending upon the glancing angle or whether your X-ray is hitting straight perpendicular to your sample, you can vary the depth information that comes from the sample. And this is an example of how when you have different glancing angles of X-rays, you can get different information from the thin films that you are working on. And the last holder, specialty holder, what we have here is called as a vacuum transfer module. So many of us, one of the recent interest and emerging interest, as I should say, is working with battery materials, particularly lithium ion batteries. So when you work or handle lithium ion materials, it is important that you don't expose them to atmosphere. The more time you protect it in vacuum, it's better to maintain the nativity of the lithium ions. So when it comes to characterizing these battery materials, it's very important that you maintain it in an inert atmosphere. And in order to manage that inert atmosphere, we have a dedicated module called vacuum transfer module. So when you have this holder, you can load your battery materials in a glove box environment, get it into this module, and this can be loaded into an XPS, maintaining the vacuum state or the true nature of the sample of these materials. So once your sample gets inside the instrument, I mentioned in our instrumentation page that there are different cameras that help you to get a view of the sample. So using those cameras, you can get different views of the sample and you can select the region of your interest on the sample. And it can be either a point, a line, or an area that you can select. Whatever you select on this image, the X-rays will fall on those samples. The stage will scan or move across, that gives the rastering, and you get information from every pixel of the sample as you scan across. So very quick information on the performances, though it doesn't really matter. This is a plot to show that depending upon the X-ray spot, your performances, your sensitivity can greatly vary. And for a very quick scan, it's a normal practice that you use a larger spot size, which is 400 microns. And when you do a 400 micron spot size on the K alpha instrument that you have, you will be getting around 4 million to 4.5 million counts per second. And whenever you want to do a very small area, it's a good practice to do it either at a 50 or 100 micron spot size. And I mentioned about insulating samples. A very quick message in terms of instrumentation, what happens. When you have a non-conducting sample, an insulating sample, the charge builds up over a period of time. So it is a requirement or a must to have some mechanism which will help you to neutralize the charge. So on a K alpha instrument, you have a charge compensation system, which is a dual gun type. The reason I say a dual gun type, you have an electron emitter, and this electron emitter gives you negatively charged electrons. Along with the negative charged electrons, you also have an inlet which can take inert gas such as argon, and this can give you the positive ions. So a combination of positive ions and negatively charged electrons can give you a perfect charge compensation on the sample surface. And as a user, you need to just click on charge compensation on your user interface, and the instrument automatically takes care of switching on the electron gun, as well as the argon inlet. That's an automation that has come in recent days. So a very quick example that if you have a good charge compensation, even for a polymer samples, it's absolutely easy to do a scanning of XPS. This is a glorious example of polyethylene terephthalate, which is a sort of a standard sample to demonstrate the performances of an insulating sample. The beauty of this PET sample is that around the 280 to 285 edge, you will have 3 peaks of carbon, And these 3 peaks are called as the ester peaks in the XPS library. So as long as your instrument has a very good charge compensation, then only it is possible to identify 3 individual peaks. So always when you have a non-conducting sample, it's a good practice to check the performance of an instrument with a standard sample before you start recording any insulating samples. So moving on, I'm coming to the last part of my talk. When you load a sample, particularly knowing that XPS is a very surface sensitive technique, it always becomes a little bit of a question mark to us. Where do I start my XPS analysis on my sample? Because when you take 2 mm or even powder samples, it's always tough to decide what is my right region of interest. And this question remained for many, many generations on the instrumentation. But recently, thanks to the advancements what we have with the camera technologies, it is always possible that you can do an XPS mapping of your sample. When you have a sample, you collect quick photoelectrons, and based on the photoelectrons, you plot the chemistry of a sample in a very quick time. When you have the chemistry of your surface, as you see here, then it becomes easy for you to decide where is my region of interest, where should I start my scanning. And this is called as an XPS or a chemical mapping under an XPS. A very good technique to have. And in most of the literatures today, these days, you will find this kind of beautiful chemical maps that start appearing in journals. And this is not only for a small area that you can do a chemical map, even for a large area like a 60 mm by 60 mm stage, also you can do a chemical map. The only drawback is larger the area you go, longer the time it takes to complete the scan. And coming to the last topic, a quick recall. XPS is a technique which gives you information from the top 10 surface, but not all the problems, particularly the modern age problems, they lie on the surface. Particularly with all the materials that are coming up in recent days, the surface plays a very important role, but it's also important to understand what is the interfacial chemistry beneath the surface. And that's an interesting study that is coming up more and more, particularly with these modern age materials. And when we talk about these kind of studies, here is an example where you have a substrate and you have multi-layer films. So now, using XPS, you get fantastic information from the surface. But the modern age of researchers, they'd like to have what is the chemistry on the surface and what is the interfacial chemistry as we go down through the surface. And that's where we have a beautiful experiment called the depth profiling experiment. The depth profiling experiment helps you to remove material in a very controlled fashion. And it's not only about removing the material. As you remove the material, simultaneous recording of the chemistry also keeps going on. So you remove the material and understand the chemistry as well. So for example, if you have a certain films which has a carbon and fluorine and carbon and oxygen beneath, which are just 2 or 3 nanometers apart, you can do an XPS. And that's the sort of depth profile that you will get. You will first get the curve with the fluorine, and then you start getting the oxygen maps. So this is a sort of a study you need to bring in as a practice whenever you do XPS analysis. And as we go forward, we can do it even for a larger areas. For example, the hard disk that we use day to day, this hard disk has multiple layers starting with the glass substrate. On top of the glass substrate, you have different layers which have different conductivity nature. And when you do a depth profiling, you not only understand the chemistry, but you also understand the interfacial chemistry between these layers. You can understand the diffusion of these layers as you go across, and that gives you a complete overall understanding of the sample that you're trying to run through. And the last topic that I would like to cover today is like all these techniques, whatever we have seen so far, they are X-ray photoelectron spectroscopy, which means you are using an X-ray energy of 1486 eV. There is another complementary technique which can be attached with an XPS, is called UPS, ultraviolet photoelectron spectroscopy. So this UPS attachment is available on your K-alpha instrument, and what it does is that it uses a helium lamp. And helium lamp can be used to target and scan across your sample, and it gives you a completely different set of information from your sample. Why do we need to use an helium is that you recall the X-ray energy is 1486 eV, quite good enough to knock out the electrons from the core shell. Now, when you use an helium, the energy of this helium stands at 21 eV, which is very, very less. And this is sufficient only to knock out the valence electrons from the outermost shell. And these valence electrons, they give you a very useful information about the valence band of your sample. So when you know the valence band, it also gives you an information about the HOMO and the density of states information from your sample, which are very critical, particularly if you're working on band gap studies and semiconductor samples. These kind of complementary techniques also help our understanding of the sample to the next level. So now the last topic is that you can combine this UPS depth profiling all together. You can automate them. So the instrument collects XPS information from the surface. It removes material from the surface. It gives another XPS spectrum. It transfers it to the UPS. You start getting multiple information from the same time. So as a user, in a given amount of time, you end up having a plenty of data, which is a wealth to understand the information about the sample. And all these techniques, whatever I spoke about today, you are able to record it with a single software, which is called Avantage. So this Avantage is a single platform which helps you not only to collect data, it helps you to process the data, and more importantly, it guides you to interpret and understand the data as well. So in one sense, K-alpha has been an instrument which has been a path breaker, enabling XPS for every single user. It not only enables analysis on a wide variety of samples, but the information what you get out of it, XPS, is not only automated, but it helps our understanding of the sample to the next level. So with that, I quickly conclude by showing the different models available with Thermo Fisher Scientific. K-alpha is the instrument what you have in Center for Advanced Studies. You have another model, which is a next generation of NEXA, what we call it as next generation surface analysis. It does all that an K-alpha can do, adding to few complementary techniques. And finally, you have an ISCA lab, which helps you to do in-depth analysis of an XPS for every single complementary technique which can be done on the platform. So if you'd like to have more queries, I'm very happy to discuss with you. And once again, thank you all for this wonderful attention and inviting me here. Thank you all. Is there any queries I can address? So the only way is to remove the moisture content of the sample. The moment you have moisture content, it disrupts the vacuum setup. So you need to dry out the moisture content out of your sample. Sir, for biological samples, I'm not aware of it. Yes. It can go as much as you can allow the time, sir. Because when you want to go few hundreds of, it depends on the time you give for the instrument. For few tens to hundreds of nanometers, it takes minutes. But if you go more and more hundreds of nanometers, then it gets into hours. And if you want to get into hundreds of microns or millimeters, then we are talking about days of experiment. Yes, you can do. Yeah, not with the UPS, with the standard XPS also, it's a straightforward measurement, understanding the oxidation states. You can do that. Yes. Thank you. Yes. Sorry, ma'am, I'm not able to hear you. Even for bulk metals, you can use any kind of a sample as long as it is vacuum compatible. The only thing you need to be cautious is that the information what you get is coming from the top surface, top 10 nanometers. So irrespective how bulk your sample is, your information is from the surface. Yes, you can do that. Yeah, you can do that. All those are standard techniques. What can be done. And what I would recommend you all is that there is a website called xpssimplified.com. So when you want to understand more about XPS, its basics theory, or you want to understand even about the data interpretation, xpssimplified.com is a fantastic resource to utilize on. And particularly when I was a student, that was a website that helped me a lot to get my understanding better on XPS. So I would strongly recommend each of you to go through that. Yeah. Ma'am, it's not about biological or material sample. Let me put it this way. As long as your sample, irrespective any sample you have, as long as your sample is vacuum compatible, it is not degassing, then it's good to go in under an XPS. I think, thank you all very much. Yes, please.
As a research, what should you suggest that what should how we can make our sample analysis in XPS? Example, powder sample. So some other stuff is coming into the graph. So how to analyze the graph and how to avoid taking the sample?
In fact, for an XPS, you don't need any sample preparation. Particularly if you're using a powder sample, you don't need to have any preparation. If you remember one of the holders that I showed, most of your contaminations on powder samples comes from either cross-contamination or the contamination what it picks up from the sticky tape, double-sided carbon tape. So if you're using a double-sided carbon tape, use a very, very small quantity of your powder. If not, go for the dedicated powder sample holder. In fact, this is one query you can post in the next session on data interpretation, where we can discuss on that. Thank you.
That is qualitative. But you also talked about quantitative.
When you compare XPS with other quantitative techniques, for example, if I take a EDS which is attached to an SCM, or you can take an XRF, these are the techniques which will have a sort of inaccuracy plus or minus 1 to 1.5%. Whereas XPS is a technique which will give you an accuracy much better than 0.5%. Because here it is a very specific narrow region technique and it gives you from the top surface, and the quantification what you get out of an XPS helps you to better index your samples. The quantification accuracy is much better than any of the other analytical techniques which is available. We do have a software. The software helps you to quantify it. It's based on the number of electrons, photoelectrons that you collect. It's a ratio of intensity ratio, what it is plotted. Absolutely, yes. We do have standards against which the instrument is calibrated. Correct. Yes. Not like that. We will do our calibration on standard universal samples. The instrument will be calibrated, and when you have a calcium sulfate, depending upon the chemistry what you have, the composition will vary. And this is a composition statistics which the software will help you to get it. Yeah. Just like any other technique, like a EDS which is attached to an SCM.
For his type of sample, is XRF a better choice?
Sir, ideally speaking, both the techniques, because the information from XRF is from the bulk. It's about 100 to 150 microns beneath the surface, whereas the XPS information is from the surface. So ideally, both these techniques, they will complement each other. Sorry, can you build? Yes, very nice. Because all these hemispherical analyzers, you will find it like a oval. Because when you have it as a oval shape, it helps you to better bias the photoelectrons towards the detector. Because when you have it as a cylinder, probably you are not getting as much accuracy of controlling the photoelectrons that travel. Whereas when you have an hemispherical setup, it becomes much easier with the electrostatic lenses to control the trajectory of these photoelectrons. That's the reason almost every supplier has switched over to having an hemispherical analyzer. Yeah. Thanks for asking that. So with that, I'll wrap up. Thank you very much once again.
Sir, thank you, sir.